Thank you always. And the slides. No, not this one. Hold on. Okay. Share screen. This one. Okay, can you see it? Okay, good. All right, so let me get started. Sorry that it was a little trouble. I announced the idea of the midterm, so it's going to be posted this Friday. And so by then, of course, the current homework will be due, and then you have a week to actually finish this take-home midterm exam. So I explained that all to you already. So let me get back straight to physics. So we started to talk about the superconductor. I already mentioned this idea that pair of fermions can become sort of a Bose-Einstein condensate. And so that's the idea of what is called the BCS state. It's sort of a loosely bound state between two fermions where one fermion has momentum P, the other fermion has momentum minus P. Overall, this pair has no momentum at all. And these pairs of fermions would have a macroscopic number going into the zero momentum state, even though individual fermions, of course, have to occupy different microscopic states because that's not allowed by the Pauli's exclusion principle. So that's the idea of the BCS state. We talked about how the wave function looks like and so on. So that's the idea we're using for the superconductor. So the idea mentioned in the case of the superconductor is that if you have an electron moving inside the lattice, then lattice would deform because of the Coulomb attraction between the electron and positively charged ions. So where electron is, looks as if has a net accumulation of the positive charge if you look at it from afar. So the other electron far away can get attracted to the electron together with this cloud of the positive charges around it. So that's the origin of the attractive force between two fermions, in this case, two electrons, in a piece of, for example, metal like niobium. And then we want to write down the Lagrangian for it. So I recall this kind of modern view of the quantum field theory that we resort to the ideas of symmetries, and we write down the motional Lagrangian consistent with those symmetries. And so one of the important symmetry we started to talk about last week is the gauge invariance. So from this point on, I start to go slowing again, but any questions about this idea we talked about last week on how to deal with the system of the Cooper pairs of electrons inside a lattice, which end up being in this sort of condensed state of the BCS state. And we are trying to write the motional Lagrangian consistent with the idea that it has to couple to electromagnetism in a way consistent with the gauge invariance of the electromagnetism. So I see somebody moving there. Who's that? No? No questions? Okay.
Professor,
Oh, go ahead.
there's this like small notification boxes, like on the right below of your screen. Can you somehow like shut it down because it somehow blocked some of the formula?
Okay. I think this one. Is it gone now?
Oh yeah, it's gone.
Okay, good. Thank you for pointing that out. So anyway, so we wanted to use the idea of the gauge invariance of the electromagnetism to fix the form of the Lagrangian for the field that describes the condensate of these Cooper pairs of electrons. And just a refresher here, so the field strength of the electromagnetism, electric field and magnetic field are written in terms of the scalar potential phi and vector potential A. And at least in classical mechanics, everything depends only on the field strength. Nothing depends explicitly on the scalar potential and vector potential. So in some sense, scalar potential and vector potential are sort of mathematical artifacts, and physics doesn't depend on them. And so if you can actually change both scalar potential and vector potential using this arbitrary function chi, so that the scalar potential changes by minus chi dot and the vector potential changes by the grad chi, then these changes would not modify the electric field and magnetic fields, and therefore doesn't change physics. So that's an internal operation on the scalar potential and vector potential by arbitrary function chi, so that physics doesn't change according to these changes of the scalar and vector potentials. And this is the origin of the gauge invariance in classical electromagnetism. So electromagnetism, and therefore physics, is independent of gauge you pick, namely that you can choose this function chi in a way you want to simplify your calculations. And so that's the idea of the gauge invariance. So what we need to do, make sure that is that when you go to the quantum theory and the field theory, you still have this gauge invariance, namely that by changing phi and chi, A by arbitrary function chi, physics doesn't change. So that's what we need to require. And we started to review how that actually works in the conventional Schrodinger equation, looking at the examples on quantum mechanics. And so this is the single particle Schrodinger equation you have in the presence of the vector potential, like in magnetic field, and in scalar potential, like in a Coulomb potential. And what I told you is that this equation is actually covariant when you notice that this combination of P minus EA is actually this derivative operator. And as you see on the next slide, this particular combination of the spatial derivative and the vector potential is covariant. And I will define that again, once again, on the next slide. In a similar way, if I use the scalar potential to the other side of the equation, I have this particular combination of the time derivative and the scalar potential. And again, this particular combination has this property called being covariant. So the covariance means if you actually perform gauge transformation of changing A and phi, like on the previous slide. But if you, in addition, change the phase of this wave function psi by the same function chi, now in the exponent, so that this is the change of the phase of the wave function in a way that depends on space and time, because chi is an arbitrary function of space and time. So this is what we call the local operation. It's not constant phase, but it's a space-time dependent phase. So if you do this space-time dependent phase change of the wave function together with the gauge transformation of vector potential and scalar potential all at once, then the Schrodinger equation maintains the same form, except that the both sides change by this phase factor. So the Schrodinger equation is not invariant. It does change, but the change is just an overall factor, the same factor on both sides of the equation. Then you can drop the same factor from both sides of the equation. So you go back to the previous form of the Schrodinger equation. So somebody was asking you this question on Piazza, which I haven't responded to yet, I'm sorry. But the difference between invariance and covariance is just what I said. If something is invariant, after doing these transformations, it doesn't change at all. In this case, Schrodinger equation is covariant. The co means together, right? So covariant means the equation does change, but changes in a way that goes together, that both right-hand side and left-hand side of the equation change by the same phase, again, together. So that's the meaning of covariant form of the transformation on the Schrodinger equation. And therefore, again, physics doesn't change before and after the gauge transformation. Okay, any questions about this?
Professor, I think there's a small typo in the second equation of those covariant derivatives, because I think there's a minus sign between IH bar, like partial t, and E phi. Because if you multiply IH bar inside the brackets, you got the I squared, then this should be a minus one, right?
Can you point to which equation are you talking about?
Yeah,
again?
this one. Yeah, this one.
The bottom one?
Yeah.
Okay, and what is it again?
I say if you multiply IH bar inside the parentheses, you get I squared, right? And I squared should be minus one.
I see. So you're talking about this plus sign.
Yes. And
Yeah.
for me, like this one is just like moving the E phi psi from the right hand side of the Schrodinger equation to the left hand side of the Schrodinger
Yeah, I
equation.
believe
So,
you're right. So this must be a typo. Yeah. Thank
okay.
you for pointing that out. I'm going to fix that later. Any other questions or comments, complaints? All right. And so what we learned is that this combination is special, and we wanted to see that explicitly here. So the idea is that when you have this combination, P minus EA, or this derivative operator acting on psi, after the gauge transformation, I'm supposed to change psi to psi prime and A to A prime. So this is the form after the change. And this A prime is given by the transformation we figured by looking at the electric and magnetic fields 2 slides ago. So we know what that is. We also have specified what psi prime is in terms of this phase factor. And now that this gradient would act not only on the wave function itself, but can also act on this phase chi that pulls out IE grad chi over h bar with a positive sign, which cancels this grad chi with a negative sign in the change of the vector potential. So that's why this is a special combination where this chi grad chi cancels in this parentheses, and end result is that the whole thing changes by a phase factor. So that's the meaning of this combination being covariant, and therefore this thing in the parentheses, which is a derivative operator, is called covariant derivative. And the same thing is true with the time derivative. Again, you change both phi and psi according to the gauge transformation. But again, remembering that phi prime is given by phi minus chi dot. Psi prime is a phase change of psi. And this time derivative not only hits psi, but can also hit chi that cancels this chi dot coming in the gauge transformation scalar potential. The thing in the parentheses go back to the previous form we had before, and the only change is this overall phase factor. So once again, this combination in parentheses is called covariant derivative. It's a derivative operator in time, and it has this nice property that after doing gauge transformations on everything in here, the only thing that happens is an overall change of the phase. So that's the meaning of covariant derivatives. Again, we talked about this last week. I'm just reviewing it once again. Any questions about this? No, these things are look kind of strange the first time you see it, but now that you're seeing it already second time, I hope that it will start to sink into your mind. And I'm curious to know, was this kind of thing being discussed in quantum mechanics class when you talk about Schrodinger equation with vector potential and scalar potential? Ryan is nodding, some others are not. So maybe it varies. Okay, but I hope this makes sense now. So the idea then is that the Schrodinger equation as a whole is covariant, as I claimed 2 slides ago. So if you have this covariant derivative on time of psi, given in terms of this covariant derivative squared in space acting on psi, this is the free Schrodinger equation in the presence of the external background, scalar potential, and vector potential. So that's something I believe that's familiar to you. And if you change everything, phi to phi prime, psi to psi prime, a to a prime, this is the new Schrodinger equation. But using the property of covariance we checked on the previous slide, then you know all the changes there is in the end is that left-hand side changes by overall phase. Now everything back to where you started. On the right-hand side, again, it's just an overall phase factor where everything else goes back to where you started. And hence, the Schrodinger equation is covariant. It does change, but it changes together by the same phase factor on the both sides of the equation, and hence Schrodinger equation is covariant under the gauge transformation. Then you can cancel the same phase factor from both sides of the equation, and then physics doesn't change. So that's the reason why we can still use the same gauge transformation we learned in classical electromagnetism, still at the level of the quantum mechanics. So that's the progress now. We went from classical mechanics now to quantum mechanics. Now we need to move into quantum field theory. Okay, again, let me stop here for the moment if there are any questions. Okay, good. So now we go to the field theory. So in order to write down the Lagrangian in field theory for the Schrödinger field psi, which we have done already many times by now, you have dealt with in writing down the quantization, multiparticle wave function, and so on and so forth. So what we learned is that the Schrödinger field theory Lagrangian has to be invariant under symmetries. And we verified this in the case of the Galilean transformation by going from one reference frame to another. And there, it was important that the derivatives comes in this combination of time derivative and spatial derivative squared. And we made sure that Lagrangian is invariant, not covariant, it has to be invariant. And we do the same thing here for the gauge transformation. Now that we have this combination, which we know transforms nicely by an overall phase factor, we use this combination as the building block to write down the Lagrangian. And by doing this way, then we know this combination of this derivative acting on psi changes by an overall phase, while this combination of the complex conjugate also changes by a phase, but with the opposite phase because it's a complex conjugate. So the product of this covariant derivative acting on psi dagger and this covariant derivative acting on psi changes phase in opposite directions, so they cancel in the Lagrangian, and therefore this term is invariant under the gauge transformation. So that's basically the idea. So we change psi to psi prime in the Lagrangian everywhere. So this psi dagger becomes psi prime dagger. This psi becomes psi prime. This one, that one, and all of these four, they all change in the same way. And we also change phi and A in the same way we learned from the classical electromagnetism. And if you do all of them together once, then we know this combination transforms nicely, covariantly by this single phase factor, which cancels every time that appears because this change in phase over here cancel against each other. We already know that this change of psi to psi prime leaves these terms invariant because, again, you always have the same number of psi and psi dagger in both of these terms. So this phase coming from psi is always canceled by the opposite phase coming from psi dagger. So these two terms are invariant. We know that already. Finally, we look at this term here. And once again, this is the covariant derivative. So this combination changes by the overall phase, while psi dagger changes by the opposite phase. So the phase factor cancels. So this first term is invariant too. So as a whole, this Schrödinger field theory Lagrangian is invariant under the gauge transformation we talked about. So that's why we use this Lagrangian, because this is pretty much the only Lagrangian you can write, which is consistent with the gauge transformation. So in some sense, we don't need to know much details about the material we are dealing with. Once you know that electromagnetism needs to be gauge invariant, then that dictates what kind of form of Lagrangian we can write. And so that's a very powerful tool we can use in quantum field theory all the time. Once you know the symmetries, that restricts what kind of form of Lagrangian you can come up with, and then you can analyze it and its consequences. So that's the modern views of quantum field theory I mentioned a few slides ago. And now we are implementing that idea to write down this Lagrangian for the field that represents the Cooper pairs of the electrons. Okay, so let me pause here again to see if there are any questions about this general idea.
Oh, yeah, I just wanted to clarify that. So we've kind of taken into account Galilean and gauge invariance, in kind of a two-step of we have the original combination of Galilean invariant derivatives, and then we've substituted the specific time and space derivatives that make it gauge invariant.
That's right. Thank you for asking the question, Anna. Any other questions? Okay. So now we got this Lagrangian. And once you have the Lagrangian, you can write down the Euler Lagrange equation, and you are doing that. And suppose you're looking for a solution in the absence of these external electromagnetic fields, then the equation looks exactly the same as the Euler Lagrange equation we solved in the case of the Bose-Einstein condensate of cold atoms. So we know the solution. Here's the static solution, where psi acquires a value of the square root mu over lambda. So we learned that mu over lambda has the meaning of the number density of this field psi. And you can also go to a moving frame that this is now a solution to the Euler Lagrange equation that represents the constant flow with the velocity v. So we have these solutions, which we can use once again in the case of these Cooper pairs in the piece of superconductor. So what this solution represents then is that what is called the supercurrent, because this is an electric current, because psi carries electric charge 2e, representing the Cooper pairs of electrons. And that object with charge 2e is now flowing with the velocity v. So this is a superfluid. It is fluid, but it carries the electrical charge, and that's why we call this supercurrent. So this is the phenomenon that once you go to low enough temperature, certain metals, even some organic materials, show this superconductivity so that the electric current can flow without any resistivity. So there is no energy loss. And this sounds really fantastic. And this is still in the process of the research and development. But in the future, we probably are going to use superconductors for the electrical grid. The transferring power from the power station to your home, right now, we lose a lot of power just because of the resistivity in the wires. But once you use the superconductors as a way of transporting power from power stations to your home, then you don't lose any energy. So that will be far more energy efficient, and there's a far less loss of energy. And so we end up using probably less fossil fuel in our power plants too as a consequence. So that will be a very, very good thing to have. Unfortunately, these superconductors we have today still have some problems. Many of them have to be cooled down to the temperature of a few kelvins. And that's the liquid helium kind of temperature, not liquid nitrogen. So that's very difficult to achieve on a big scale of building power lines. So that's one problem. There are other kinds of materials called high TC superconductors, and which have much higher critical temperature. So you don't need to go down to a few kelvins. You can be at as high as 70 Kelvin, nearly 100 Kelvin. Then liquid nitrogen is good enough for the purpose of keeping the material superconducting. So that sounds great. But unfortunately, the kind of material we have for these high TC superconductors are in some sense kind of the ceramic objects, and very brittle and very difficult to build cables out of them. So that's why it hasn't become really practical yet on the large scales. So this is still a research going on, either to increase the critical temperatures for the material that are easy to deal with. And one candidate that came out recently is called iron-based superconductors. So that's a candidate that might become usable at higher temperatures, and the iron steel is very easy to manipulate with. Or we somehow deal with this sort of ceramic material of the high TC superconductors in a way that it's no longer brittle, and we can bend and route and manipulate with it. So either way, we will have this possibility of lossless transfer of power. So hopefully that would happen, and this is really the basis of that. But even before going to that far future application, we are already using superconductors on many different applications. For example, if you go to hospital for cancer therapy, now so cancer diagnosis, often you use MRI, and MRI relies on strong magnetic field to manipulate the nuclear magnetic moments in your body to understand basically the composition of your body and where the cancer cells might be and so on. And for the strong magnetic field, to create a strong magnetic field, you need to run a strong electrical current. But once again, if you have a big electric current flowing in a material that has a resistance, you keep losing current. And that would create a huge amount of heat, which you cannot deal with. So already in hospitals, people are using these superconductors to run current without any resistivity. Therefore, it doesn't produce heat, so you can keep it cool. And yet, it has a high electric current flowing through it, and therefore you can produce many Teslas of the magnetic field applied to your body, and so that it's strong enough to manipulate with your nuclear magnetic moments so that you can understand the composition of your body in a three-dimensional slices. So that's something already that's used very in a practical fashion in hospitals. And another sort of a still not quite common, but application that is starting to appear is the maglev. So if you want to have a high-speed trains, and if the train is running on a rail, then it shakes so badly that people will be vomiting all over. So you don't want to be on that kind of train. So the idea is to let the train float. And if the train is floating in the air and just gliding through it, then it doesn't shake very much. But in order to float an entire train and let it also move forward in a levitated state, then you need, again, use a lot of electric current and magnetic field. And the use of the superconductor is the way to go. So as a matter of fact, Japan is building a new maglev system right now, and that is really relying on the superconductivity to make it float and still being accelerated in this levitated state. And so that is coming into practice. So the superconductor is not the fictitious thing anymore. It is being used in a practical fashion for many different applications, not the least, as to mention, this high electromagnetic field you need for Large Hadron Collider at CERN to accelerate the beam of the proton up to incredible high energy. And you have to keep bending it in this 17 miles circular tunnel. So it's going with very high speed, high energy, but in order for the beam to keep going inside the tunnel, you have to keep bending it. And for that purpose, we need to use 8 Tesla superconducting magnet. So that's one sort of the largest scale application of superconductivity we know on our planet today. Okay, so these are just talks, but I hope that gives you an idea that this thing is actually a practical thing. Any questions about that? No questions? Okay, so the formalism is exactly the same as we have done before with the BEC, so there's nothing new on this slide in some way. So the only difference is with the interpretation, that this is now a supercurrent rather than superfluid. And then we discussed this very briefly the last time, and it was very quick, so I'd like to go much more slowly this time, and then you're actually looking into this in homework as well. So in addition to the Lagrangian of the Schrödinger field that describes these Cooper pairs, we also add Lagrangian for the electromagnetic fields. And we have the epsilon and mu. These are constants in electromagnetism, you know, magnetic permeability and dielectric constant, if you have some material around you. And in the vacuum, we put the subscript 0 on top of this, right? Epsilon naught and mu naught. But in material, they can be different from the vacuum values. So I removed 0 from this expression. And from this, you can derive the Maxwell's equation. So maybe you haven't done it when you studied electromagnetism in some of the earlier classes. So, but it turns out that this Lagrangian is what gives you the Maxwell's equation. So you take the variation of this Lagrangian with respect to scalar potential and vector potential. And by doing so, you can derive these Maxwell's equations. So that's the idea. And two of the equations are actually something that comes straight from the definition. For example, divergence of B vanishes simply because B is written as the curl of the vector potential. And divergence of the curl always vanishes, which is something you have learned in vector calculus, I believe. So this is just a consequence of B written in terms of the scalar potential and vector potential. And this equation is also the same. E is negative phi dot minus A dot. B is curl A. If you plug them in here, this equation is automatically satisfied. So this second equation and third equation among the Maxwell equations just come out from the fact that E and B can be written by the scalar and vector potential. So these two equations don't rely on the Lagrangian we have over here. So there is some sense automatic consequence. But the first and last equations do come from this Lagrangian. So if you take the variation of this Lagrangian with respect to scalar potential, then you find this divergence E. Because E contains grad phi, you use the equation, the integration by part to let the grad act on the other E that becomes the divergence of E. So that's how you can get this divergence of E from this Lagrangian. But now that we are taking variation with respect to scalar potential phi, here's another occurrence of phi in this entire Lagrangian. So that will pull out psi dag of psi. And that's nothing but this charge density rho. So divergence of E given in terms of charge density comes from this term, E squared in the Lagrangian. And also this term here, psi dagger minus 2E phi psi. When you take variation with respect to phi, you get this right-hand side, which is 2E psi dagger psi. So that's how you obtain this first equation. And this is nothing but the Gauss's law. In the last equation, you obtain by taking a variation of this thing in the parentheses with respect to the vector potential A. And vector potential appears both in E and B. Inside E, the vector potential appears as A dot. So you use the integration by part to let the time derivative act on the other E. So that's how you get this E dot. On the other hand, when you take the variation of B with respect to A, you get a curl. Again, you do the integration by parts to let the curl acting on the other B in this B squared. And that's how you get this curl B. And that's what you are deriving in a homework problem right now. So from E squared and B squared, I get this curl B and E dot. That's the left-hand side of the Maxwell equation. But now looking at this first line from the Schrödinger field, there is vector potential in there. So when you take the variation with respect to vector potential, this piece here will give you a contribution. And that's this J over here. So that way you can justify that J that appears in the last equation comes in this particular form. And let me emphasize once again, gauge invariance told us that this has to be the form of the Lagrangian. So we know how exactly vector potential enters into the Lagrangian of the Schrödinger field. Then, in order to derive Maxwell's equation, all you have to do then is take the variation of the Lagrangian with respect to vector potential. Because we knew the form already, we can derive the form of the current with no further assumptions. So everything is now forced on us. The symmetry is very powerful. Once you know the symmetry, namely in this case gauge invariance, you can derive what is the form of the electrical current should be. And that's what you're actually working at right now. So at the end of the day, we find this last equation of the Schrödinger equation is given in terms of curl B E dot given by J. And then if you specialize the form of the J in the presence of this condensate psi of the Cooper pairs, then psi for a superconductor at rest is static, doesn't depend on space and time. So the gradient vanishes. Here again, gradient vanishes. But the condensate, substitute this psi to be a constant, square root of mu over lambda. Psi of psi is the number density. That's again a constant in a piece of superconductor. So you find this weird expression now that electrical current is proportional to the number density of the Cooper pairs times the vector potential. And this is something new. And I believe we have never seen this kind of form before, anyway, in electromagnetism. But that's the consequence of this form of the vector, electrical current in the presence of the condensate of psi. And this has an enormous consequence, because once you actually plug that in here in the Maxwell's equation, you find this equation if you write out what this curl B is in terms of vector potential. And I'm still talking about static situation. And I forgot to say that in a homework problem, Anna pointed that out, so I put that into the revised version of homework problem. So in static problem, there's no time derivative, so you can cross this out. So E dot is not there. So curl B has to be given by this current J. Curl B is given by this form of the vector potential. That's just a vector calculus. Now J is given in terms of vector potential. That's something we just found out. And let's choose a Coulomb gauge. Then you find a very simple Poisson type equation that the Laplacian of the vector potential is given by a constant times the vector potential. And solving this equation is very easy. It's just an exponential form. And again, I forgot to write the assumptions behind this solution in a homework problem. What I'm assuming here is that the superconductor occupies half of the space where X is positive. So I guess from your point of view, I think X positive is on this side. So here's a superconductor. And this is the boundary. And there's no superconductor over here, but just a magnetic field. So that's the situation I have in mind. So for negative X, free space, magnetic field, and therefore vector potential. The question is, how much does this vector potential outside the superconductor gets into the superconductor? That's the question we're asking here. And using this solution, that's the equation, you can easily work out that it has this exponentially damping behavior, where this characteristic length scale for this exponential damping called London penetration depth. London's the name of the guy, not city London, the Mr. London. I came up with this idea of the penetration depth. So this is how much deep magnetic field can get into and penetrates into the superconductor. That's why it's called the penetration depth. And so by using this equation, you can work out what the penetration depth is. And in the unit of this penetration depth, magnetic field gets weaker by a factor of E for every step of the penetration depth. So it very quickly gets smaller into the superconductor. And that's the famous Meissner effect, which you might have done in the lab, 101 lab, physics 101. If you have a piece of superconductor, then magnetic field gets repelled by the superconductor in the middle. So near the surface, it's not completely repelled. It does get in, but only over a skin of the superconductor by this London penetration depth. And that's how you can understand this famous Meissner effect from the quantum field theory point of view. So this is, again, I hope you have seen somewhere in your lab classes, and that's something you can now understand just by knowing the fact that you have these condensate of Cooper pair electrons, and they have to respect gauge invariance. And that's pretty much all you need to know. Then you get this consequence that the magnetic field gets repelled by a superconductor. Okay, let me pause here. I think I bet there are many questions at this stage.
Professor, can you explain why the grade psi is 0 and grad psi dagger is 0 in the expression of the current?
Yeah. So that's a very good question. So I made one assumption. assumption I made is that the magnetic field is weak. So I start with static superconductor, where psi is just a constant square root of the chemical potential over the coupling lambda. So that's a superconductor I got. Then I apply a very weak magnetic field on top of it. It's so weak that I don't expect the psi to change very much yet. But from the point of view of the magnetic field, this constant psi has a huge consequence that you get expelled. Again, this is one of those words in physics that makes you feel very exclusive. You know, we have to make physics more inclusive somehow. So what is the right word? Magnetic field gets not expelled. Can anybody think such a better word than this? Magnetic field is social
redirected.
distancing. Redirect. I like that one. Okay, good, good. So magnetic field is redirected by the presence of superconductor. And for the magnetic field to get redirected, this is, you know, zeroth order effect just by having this constant psi. So it's already there, even when magnetic field is weak. On the other hand, the impact of the magnetic field in psi is expected to be minimal because I turned it on only by a slight bit. If you crank up the magnetic field, then I start to have to resolve the Euler-Lagrange equation for psi together with the magnetic field, then becomes a nonlinear equation. And I can't do that very simply on a piece of slide anymore. So that's why I'm making the assumption right now that the magnetic field applied is so weak that the change to psi as a solution to Euler-Lagrange equation can be ignored. But nonetheless, we already see this big impact on the magnetic field being redirected. I really like this word. Anna, that's a great idea. Anything else? So I hope this slide makes you happy. I hope you have seen Meissner effect elsewhere in the lab. Now you can explain it to your friends how that works, right?
Sorry, just one thing. Can you just, I missed it. Can you explain why we got rid of the div A, grad div
This
A
one here
term? Yeah.
Yeah, I use Coulomb gauge.
Okay, yeah, okay.
And it turns out that choosing Coulomb gauge is not arbitrary choice. So when you actually look at this form of the current, constant times vector potential, and we are talking about static problem, the continuity equation says time derivative of the number density and divergence of the current add up to 0. That's the continuity equation. We are talking about static problem, therefore time derivative vanishes. So then it requires the divergence of the current has to vanish on its own. But because number density is constant, divergence of the current is proportional to divergence of the vector potential, which has to vanish. So in this case, choosing Coulomb gauge is actually required for the consistency of the theory. So having written down this current operator in terms of the number density times the vector potential, secretly, we had chosen already the Coulomb gauge for the consistency of our calculation. And then it in turn makes this term vanish. And that's why we end up with the rest of the terms over here, namely Laplacian of A given by constant times A. And this is what is called the London equation. And as for obvious reasons, the Mr. London came up with it. Any questions about that? Does that answer your question, Anna?
Yeah, thanks.
Great. Anything else? This is a kind of important slide, so if you have any further questions, I'd be happy to take them. Maybe you have more questions after looking at the next slide. So in the case of superfluid, we talked about superfluid running inside a ring. And after removing the potential to confine the fluid inside the ring, we found vortices. So we can actually do the same thing now with a superconductor, not a superfluid, but now with a superconductor. It's a little bit more complicated problem though, because once you have this superconductor with a vortex in it, we have to solve the coupled differential equation, both for field psi and the magnetic field. So we can't solve them individually, we have to solve them together. So that's why it becomes a little bit more complicated problem. And I can present an analytic solution to it. You have to do it numerically. But the solution itself looks very simple and also very similar to what we have seen in the case of vortices of the superfluid. So the idea is that this field psi, which is a complex field and therefore has a phase, basically goes like square root of number density, but its phase can change by 2 pi when you go around the infinity of your material on an xy plane. So this phase theta would wind around the spatial infinity once. So that's again this interesting topological thing that basically you're mapping the infinity of space, which is basically a rubber band, on the space of phases, which is also a circle, like wrapping a rubber band on a neck of a bottle. So you can count number of times the phase would wrap around this the phase of the field by integer times always. So that's how you get integer quantized unit of the vortices once again, just like in the case of superfluid. So at the spatial infinity, it approaches the square root of the number density times its phase factor. But when you actually go back to the origin though, where the vortex is, then at the origin, then this phase factor becomes ill-defined because theta changes from 0 to 2 pi in a tiny circle. When you shrink it all the way to a point, it doesn't make sense to talk about the phase anymore. So the only way you can make sense out of it is when this field psi actually vanishes at the origin. So anywhere away from the origin, psi has a value, and therefore its phase, and would go around by 2 pi when you travel across the circle. But at the origin, psi itself vanishes, therefore there's no physical meaning to its phase, and therefore there's nothing ill-defined over there. So that's the behavior we talked about in the case of a superfluid, so that part is exactly the same. But of course, we have to solve the equation together with the vector potential, which of course gives you magnetic field. So that's when you have to solve the coupled differential equation, which you can do numerically, and this is the solution I got, and it looks something like this. So vector potential also vanishes at the origin and becomes a constant at the infinity. And this constant value of the vector potential goes together with constant value of psi in such a way that this combination, grad psi plus a psi, cancel at the spatial infinities. So that's how you find a solution with a finite energy overall, because there's no contribution from the infinity. And once you know that A has to cancel this derivative, and we know that the derivative comes from this angular dependence theta, you know how A should look like at the spatial infinity. And that turns out to be this value here. So 2E theta is basically 1 at the spatial infinity. But once you know what vector potential is, you can immediately compute the magnetic field surface integral, because using the Stokes theorem, surface integral of the magnetic field, which is curl of A, is the loop integral of vector potential going around the loop at the spatial infinity. So A was fixed by the requirement that this cancels this derivative acting on the phase. Once you know A, you know its line integral at the spatial infinity, which gives you the total magnetic field. So there's no ambiguity here. Everything's completely well-defined, and you make a prediction on what the total magnetic flux is. That's this green line. You integrate over the space, And that comes out to be h over 2e. And h, as you know, is a 2 pi h bar divided by 2e. And this is specifically 2e because the field psi carries charge 2e, which corresponds to Cooper pairs. And once you're actually doing an experiment and measure the magnetic flux of a vortex inside a superconductor and learn that it is indeed quantized in a unit of h over 2e, that then becomes an experimental evidence that the superconductor is really made of a condensate of object with charge 2e, not e. So clearly, it's not a condensate of single electron, it's a condensate of the pairs of electron. And that's how we got convinced that the whole idea of Cooper pairs is indeed the right one. So you go ahead, trying to bring in a piece of superconductor. You turn on a cryostat, it does become a superconductor. You apply a magnetic field, you see these vortices forming. And once you measure the magnetic flux going through the vortex, you can test if that turns out to be really h over 2e. And if it is, then you have proven experimentally that the superconductor is really made of a condensate of a Cooper pairs of 2 electrons. So that's why this Abrikosov flux, this is called Abrikosov flux, is a very important subject of study in superconductivity. And Mr. Abrikosov received a Nobel Prize for working out this solution. You were just looking on this slide on this on the plot. This is Abrikosov worked this out for the first time in history, and that was the basis of his Nobel Prize. So if you had been born a little bit earlier, then you could have actually come up with this Lagrangian, solve the equation of motion, which is very easy to do on a computer, on your laptop these days, and that would have been worth Nobel Prize, actually. Okay, any questions about that?
I actually have 2 questions.
Go ahead.
Yeah, so can you explain like a little bit about how you get this numerical result? Like, did you just like plug in the like zeroth order approximation, like square root of n e to the I theta first into the Lagrangian, and you get a, and then you somehow like plug in the a again, and you solve it and plug
That's
in,
right.
like
Yeah.
over.
So I believe you're asking a practical question here. So what we know is that psi should approach a constant value at infinity. And this is number density, so it depends on your material, but you got the constant value together with this oval phase factor that winds around 2 pi at the spatial infinity. So you know this as the boundary condition for psi at the spatial infinity. And this e to the I theta behavior is common all the way through down to tiny, the distance from the origin. But at the origin, you have another boundary condition, the psi has to vanish. So you know both ends for this solution psi at spatial infinity and at the origin. You also know this vector potential at the spatial infinity from the requirement that this would give you finite energy solution. And being finite energy means this behavior of the Hamiltonian at large distances should go down fast enough so that the integral of the energy density converges, which then tell you that A has to cancel this grad. So you know what A is at the spatial infinity, again, as a boundary condition. And for magnetic field not to have a singularity, this A in the angular direction has to vanish at the origin too. So once again, you know the both ends at the long distances and at the origin for the vector potential. And Maxwell's equation is written in terms of vector potential as a function of current. So curl A is now given in terms of psi. On the other hand, Euler-Lagrange equation for psi tells you that this covariant derivative of psi squared, which depends on the vector potential, has to vanish in some combination. So that's why it's a coupled equation. You can't solve each one of them and substitute one into the other. You have to solve them simultaneously. But if you use a numerical calculation, Now that you know both ends of the boundary conditions, you put the differential equation to your numerical code and solve what's in between at the finite distances. And that's how you get this blue curve and the red curve.
Okay, I see.
And once you have this red curve, then all you need to do is to take a curl of that and then work out this green curve for the magnetic field. And once you have the green curve, you can do a surface integral of the green curve to compute the total magnetic flux. And of course, we knew it from boundary condition that this surface integral B really does need to come out to be h over 2e. But indeed, once you have the numerical solution, you can check that. You can numerically integrate the magnetic field and verify that it does come out to be h over 2e, which I have done in my own code. So does the process make sense?
Yeah. And so, yeah, you just said during that just short explanation, you said the A should cancel the grad psi, right? Up to some
at the
constant.
spatial infinity, yeah.
Okay, up some. So and in spatial infinity, like grad psi should be like 0 because these reach a constant, right? But A.
No. So
right.
the psi contains this phase dependence, which depends on the angle. So this is still a function of space at the spatial infinity. So theta is arctangent y over x.
Okay, so the psi in the picture is just like the magnitude of psi and stuff.
So grad psi is not 0 at the spatial infinity, but can be canceled by A times psi, so that this combination of the energy density goes to 0 at the spatial infinity.
Okay. So my next question is, if A is not 0 at infinity, then you have a flux, a magnetic flux equal to a constant, then you have like a finite number times you have a finite A, but you integral over an infinite path at infinity at the boundary of your sample. How can you get like finite magnetic flux?
Okay, so that's a good question, and I didn't explain to you. So I normalize this A theta in such a way that the loop integral of A theta is just A theta integrated over theta without R in it. So I absorbed R into my definition of A theta.
Okay, so it has some like R1 over R1 over R squared. Like
you can say that, yeah.
Okay.
Right. So this is just the normalization I chose because that's easier to plot this way. So this surface integral of the magnetic field is an integral of A theta over theta without R on top of it. So theta integral just 2 pi. A theta is a constant. So that's how the loop integral of A theta, a spatial infinity, gives you a finite number, which is precisely this h over 2e. Is that okay?
Yeah, I see.
Well, thank you for asking the question. That clarified this point to some of the other students, I believe. And once you have this solution, now I know psi and A theta, then I can plug that into this definition of the current and plot it, and it looks like this. So now it really looks like it's a vortex, right? So the supercurrent, which carries electric charges, is really flowing around this hole. And so the origin is where you have the magnetic field. And magnetic field doesn't get into the superconductor, as you remember. So it doesn't go very far. It damps quickly, exponentially. But right in the middle of it, psi vanishes. So the origin of the vortex is not a superconductor. There's no condensate. That's why magnetic field can be there. So what we see in the laboratory is that if you have something called a type 2 superconductor, you basically apply a magnetic field to it. And somewhere in the middle, superconductivity breaks down to a normal conductor. And that's where magnetic field can penetrate through all the way through from the bottom to the top. And around it, magnetic field is redirected so that it doesn't get too much into the superconductor. It damps exponentially. And very quickly, the condensate recovers to the constant value for the bulk material. So that's what this vortex is really about. So in the middle of it, the magnetic field punches through the superconductivity because it's not superconducting at the center. It's a psi vanishes. There's no condensate of Cooper pairs. But right outside, then psi starts to turn on, superconductivity turns on, and therefore magnetic field starts damping exponentially. And because it damps exponentially, the total magnetic flux converges and turns out to have this value of h over 2e. So that's the visual representation of what a vortex should look like. So any questions about that? So next slide is the experimental data on this. So hopefully I will appreciate this better. So here you see this beautiful triangular lattice of the vortices or Abrikosov fluxes. So each black dot has a magnetic field punching through the superconductor. And I said this type 2 superconductor. There is another kind of superconductor called type 1, which has this coupling of the psi field. Sorry, this should have been actually lambda instead of g, which is smaller than twice the square of the electric charges of Cooper pairs. In that kind of situation, the self-repelling force is weak, so that these vortices would attract each other. And once you have a vortex, they tend to collapse into a single big vortex, and then entire the material would no longer be superconducting. So for type 1 superconductor, you don't have these individual unit fluxes. They get all lumped together, collapses to a big flux, and superconductivity is destroyed. But for type 2 superconductor, these vortices repel with each other, because this is the coupling lambda in the Schrodinger field that gives you repelling interactions among the fields. And so that because they repel each other, they don't come together, and they form this neat triangular lattice at the end of the day when they're in equilibrium. So this is the demonstration that what we talked about it mathematically using the Maxwell equation and Euler-Lagrange equation is something that really does happen in the real material. And this is the kind of material we use in building MRI and maglev, and hopefully eventually this power, the lossless transmission lines. And these vortices are alive. They are not static objects. So if you actually have a thin film of a superconductor and let the magnetic field apply to it, you start producing these vortices, but these vortices can move. And this is a video of that.
We are looking at an array of defects. When the magnetic field is applied, vortices are produced from the upper film edges, and the front row of defects is soon occupied. However, subsequent vortices cannot easily pass through the front row. When the vortices finally break through the line, they first jump to distant defects. When all the defects are occupied, vortices begin to enter interstices. The interstitial vortices hop from one interstice to another as far as vacant interstices remain. Vortices are hopping from one interstice to another.
So you see that
when
vortices,
all the interstices are occupied, a different kind of flow appears. Because the vortices cannot find any vacant site to hop to, they continue flowing in a single line. All the vortices in each line move simultaneously.
So you can see that these vortices are really sort of alive, right? They're dynamical objects. They can move, and they can be jammed, like what you saw, like a traffic jam. They can hop, they can flow. So these are objects that you can study, but they don't lump together because of the self-repulsion among each other. So that's the case of type 2 superconductor. Vortices repel each other. That's why they don't fuse to form a bigger vortices. And so they sort of jam into each other, like what you saw in this video. And so, this behavior can be qualitatively understood just by knowing that these vortices are dynamical objects, they repel each other, and then you can sort of understand what's going on in this video. So that's the idea of these vortices in superconductors. Any questions about that? Isn't this great? I was very impressed when I first saw this video.
Professor, I have a quick question.
Go ahead.
The video like mentions like defects. Are those defects like extra iron
That's right.
atoms?
So this material has some defects in the structure, and the vortices tend to get attracted to those defects.
Yeah, I mean, like what are those defects like?
Oh, that I don't know. Yeah, I haven't actually looked back at what the material is, so I apologize. I don't know, but I provide the link, so hopefully you can dig that out yourself. Any other questions? Okay. And so this is just a picture of how these vortices look like in terms of magnetic field, and the kind of experiment you might have done that the superconductor floats on a piece of magnet is because the magnetic field punches through this material in this kind of picture. And once they punch through, then it's not very easy for them to move away from the magnetic field, and that's how they get pinned. So the idea of magnetic superconductor floating is actually due to the fact of pinning of these magnetic fields through the superconducting material, and that's how we can understand this weird behavior of the superconductor floating a piece of magnet. And that's what we are using for the purpose of maglev in building high-speed train system. Okay, so I stop here. Any further questions on this? Okay, good. So what I wanted to actually do for the remaining 10 minutes, I may not get through this, is to actually give you a sort of general context to this weird phenomenon that is going on. We have seen multiple times already by now, superfluid, superconductor, and several other related phenomena, which come together under the name of something called spontaneous symmetry breaking. So that's what I'd like to actually tell you now. So you all know that M.E. Noether came up with this incredible theorem, which is very important to physics, about the symmetries. So she told us that if you have a symmetry, that leads to conservation law. On the other hand, once you have a conserved charge, and that conserved charge generates the symmetry. And the second part may not make sense to you now. I'm going to explain that on the next slide, but that's what we refer to always as Noether's theorem. Symmetries are very important to physics because they have to do with the conservation laws. And here are a couple of examples. So in quantum theory, both quantum mechanics and quantum field theory, symmetry is always represented by a unitary operator. And unitary operator is special because when you act unitary operator on a state and take the absolute norm of that state, then unitary operator is multiplied its Hermitian conjugate. U dagger U is 1 for unitary operator. So end result doesn't change. So namely, unitary operator is a special class of operators that don't change the probabilities. And that's why it doesn't change physics. Therefore, they can represent the symmetries of the system. So symmetry in quantum system is always represented by unitary operators acting on a Hilbert space because unitary operators do not change probabilities and therefore not physics. And here are the examples. When you have invariance under translation, that leads to the conservation law of momentum. And that's, I hope you have learned that in classical mechanics class. But in quantum mechanics, once you have a momentum operator, which is a Hermitian operator, you can write this unitary operator where the momentum operator is an exponent. If you take U dagger, P is Hermitian, A is a distance, that's the real, I becomes minus I. And therefore U dagger is U inverse, U dagger U is 1, therefore this is unitary. In general, exponentiated Hermitian operator with I gives you a unitary operator. So that's the operator we have in this case. So exponential of the momentum operator turns out to be unitary operator of spatial translation. And you can sort of see it. So if you write P as gradient, this is exponential of the gradient, I cancels, right? And exponential of gradient, if you write in theta expansion, is 1 plus gradient squared plus gradient cube, dot. And that's a theta expansion of any function for small distances. So you can see that this unitary operator really does represent translation that way. So this is the meaning of what I said on a previous slide. Once you have a conserved charge, in this case momentum, that conserved charge generates the transformation itself. So symmetry gives you a conserved charge. Conserved charge will give you the symmetry transformation. And this is just one example. The rotation symmetry is given by the rotation of space that gives you the conservation of angular momentum. When you put angular momentum in the exponent with some angle theta, that gives you the unitary operator of rotation. So that's yet another example of the conserved charge giving you a symmetry. And what we talked about both in superfluid and superconductivity is that you're talking about the change of the phase. And change of phase is a symmetry of the Schrödinger Lagrangian, and that leads to the conservation law of the number of the particles. We talked about that. We wrote down continuity equation for it. And that number operator, if you put an exponent, gives to you the unitary operator of changing the phase of the field. And I'm not explaining it here, but that's actually very easy to check explicitly, and that ends up being some of the future problem set. In the case of just flipping the sign of the coordinate, like parity operation, in switching left and right, then if you do it twice, you go back to where you were before. So it turns out that the parity is represented by a unitary operator. But if you do it twice, you get 1. So it turns out the parity operator is not only unitary, but also Hermitian at the same time. So that square of that gives you 1. As a consequence, parity operator can have eigenvalues either +1 or -1. And you probably haven't seen much about it in quantum mechanics class, but we might actually talk about this later on when you talk about actually the relativistic quantum field theory. So these are examples that symmetry gives you conservation law, and conserved quantity gives you the symmetry back. So they are really in one-to-one correspondence, so they go hand in hand together, symmetry and conservation law. So any questions about this idea? So this is what the Noether theorem is really about in the context of quantum physics.
Yes, I have a question about you being unitary operator. So for like time reversal symmetry, the representation is an anti-unitary operator. So I don't see it fits into this like category.
Yeah, so you're completely right. Time reversal operator is anti-unitary operator. So in some sense, it involves complex conjugation on top of unitary. But in terms of physical probability, you always take absolute squared. So the anti-unitary operator basically sort of interchanges ket and bra. But once you take absolute squared, it again doesn't matter. So time reversal operator is yet another class of operators which preserves probabilities and therefore physics. They are not unitary, but they still have to be unitary to the extent, except for interchanging ket and bra, and that's the anti-unitary part of it. But the idea is the same. You require the symmetry to be an operation on your Hilbert space that does not change probabilities. And once it's unitary, it is symmetry. But another way that it can be a symmetry is the anti-unitary operator and nothing else. Any symmetry in physics has to be either unitary or anti-unitary, no exceptions. Thanks for asking that question.
And okay, so and what is the generator for this like time reversal symmetry operator? like Hamiltonian?
It's difficult to write in terms of this conserved quantity, similarly to parity, because it's discrete. It's not exponential of something. It's a discrete one.
I see.
So you can write it that way, yeah. But operationally, you can define how that acts on your Hilbert space, and it turns out to be convention dependent. But nonetheless, for all intents and purposes, you can practically implement time reversal operation on a Hilbert space in a complete well-defined fashion once you specify the system.
Okay, I see. Thank you.
Okay. Any further questions here? Okay, I need to wrap up soon. So what I wanted to do is to actually give a part of my regular colloquium talks. I've given one in Berkeley too, about this general idea of symmetry breaking. And just to give you an upshot on this, I don't go through this today, but I'll come back on next Friday. Spontaneous symmetry breaking can happen in a lack of laundry, halibut, flounder, sugar, and all kinds of different systems. And we talked about superconductivity too, which actually happens to be exactly the same physics, what happens in particle physics, of something called the Higgs boson. And you probably heard of the name Higgs boson, which some of our friends working on Atlas experiment in Berkeley have discovered back in 2012, that's 80 years ago, using the Large Hadron Collider experiment. And that's the idea that Higgs boson is a particle which is in a Bose-Einstein condensate in our own universe today. Empty space is filled with this Higgs boson, and that is causing a superconductivity of the universe in such a way that, similarly to magnetic field getting redirected by the superconductivity, it doesn't go very far because of this exponential damping. That is the reason why another force in the particle physics called the weak interaction, responsible for nuclear beta decay, becomes very short-ranged. Similarly to magnetic field and superconductor, this W boson field becomes short-range. That's identical physics. So what I try to emphasize in this colloquium-style talk on Friday is how this general idea called spontaneous symmetry breaking really permeates through many, many different examples of physics, chemistry, and biology even. And superconductivity and superfluid we talked about was just two of the examples of that same concept. And Higgs boson is another one. So I try to tie them together to finish up this first half of the course on non-relativistic QFT. So that's some sense the grand finale of the first half of the course, this course. So that's the plan for Friday. Any questions about that? Good. So that's it for today. And I see you again on Friday.
Thanks.
All right, bye.
Thank you.